Okay, so let's finish up these last set of notes. We're not going to call it 3.1, just Introduction to Probability Distribution. So a few objectives here, okay? We want to construct a probability distribution for a random variable, which we will talk about what that is in just a second. And we want to determine if a distribution represents a probability distribution. So those are the two objectives for today. So let's start off with some vocab. What is a random variable? It's a variable whose values depend on outcomes of random phenomenon. So it's a variable whose values depend on outcomes of random phenomenon. A random variable is a function in algebra, or it could be represented with a function. So when we say it is a function, that means if you graph it, it will pass the vertical line test. Okay, it's just a small note. Example, a coin is flipped 3 times. Let the random variable x we'll call it x, represent the number of heads. So x equals the number of heads, right? X will be the value of 0, 1, 2, or 3. We're going to give them a few different values. So x is going to equal 0, 1, 2, or 3. 0 means there were no heads when we flipped the coin 3 times. 1 means 1 head when we flip the coin 3 times. 2 being 2 heads appeared, and 3 is 3 heads appearing. So I'm going to be linking a video for random variables by Khan Academy on Schoology. I do want you guys to watch this video. I don't know why my pen stopped working. Just 1 second. All right. I didn't realize this thing was basically almost dead of charge, so let me just plug it in. And we are charging. Okay. The pen is still not working. Why is this not working? Okay, so back to this. So I'm going to be linking a video from Khan Academy about random variables and how to obtain them. So what we do is we have a calculator and you basically let the calculator know, and I don't have a calculator on my iPad to kind of show you. So we let the calculator know, give me a random variable, 0, 1, 2, or 3, and it will generate that random variable every time for you. Okay. All right, next up is the discrete variable. The discrete variable is just a random variable that can take only a finite number of values that can be counted. So it is the random variable can take, so the random variable can take only a finite number of values, can take on only a finite number of values that can be counted. So an example of that is the number of phone calls made by a telemarketer. Okay, there's a finite number of phone calls that can be made. They can't just be making infinite phone calls. Um, these can be placed to a discrete probability distribution. So discrete variables, which are finite, right, can be placed into a discrete probability distribution table. Now, continuous variables are variables whose values are determined by means of continuous measuring scales instead of being counted. So variables whose values are determined by means of continuous measuring scales instead of being counted. So an example, we can assume an infinite number of values, which is what makes this different than discrete. We can assume an infinite number of values. So an example of this is the amount of time a telemarketer spends on the phone. So they can call one discrete variable, right? They can call one person. That is a finite number, or 10 people, but they can stay on the phone for as long as they want. Okay? So let's determine if the random variable is discrete or continuous. Hint, is the data counted or is it measured? That's kind of what we are going to be looking at. So for example, over here, when we said the telemarketer, how many people can a telemarketer call? That is 1, 2, 3, 4, 5, 10 people, 20 people, 30 people. The amount of time the telemarketer spends on the phone, we're going to have to measure that with every single phone call. So if you look at these examples, the number of books in a university library, well, obviously those are counted. So that's going to be a discrete variable. The length of time it takes to get to work, that's going to be measured. You can't count that, right? You have to measure it by driving to work. So this is going to be continuous. The volume of blood drawn for a blood test. So you won't be able to count this until you actually measure it. So this is going to be continuous. The number of tornadoes in May, that's going to be discrete. Okay, so that value has a numerical value. The exact amount of snow on Christmas in inches. Well, you're not going to know that until you go outside and you measure it. So because we have to measure it, this is going to be continuous. The amount of snow on Christmas in inches, but rounded to the nearest tenth, right? So this is just asking for the amount of snow rounded to the nearest tenth. This is actually discrete. You do have to measure it, but it is a finite value. Okay? So this is being the exact amount of snow. We have to measure it. This is what is the amount of snow rounded is going to be discrete. This is going to be the topic of questions. Honestly, like it's our examples are not going to be this difficult. It's going to be a little bit more straightforward, like the first four. Now, what is a probability distribution? Well, a discrete probability distribution is the probability associated with all values of discrete random variables. So it's the probability associated with all values of discrete random variables. So it's performing the experiment using random variables and getting their probability. So let's construct a discrete probability distribution for the probability of experiment of tossing those 3 coins that we talked about earlier. So our sample space, when we toss 3 coins, okay, our sample space when we toss those 3 coins, we're going to have either all tails, right? Tails, tails, tails. Let me fix that. So we're either going to have tails, 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 or we're going to have tails, tails, heads, or we're going to have tails, heads, heads. We're going to have heads, heads, heads. So where are we? Let's make sure we get all of them. So tails, tails, head, tails, 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 heads. Tails, 1 tails, 2 heads. Remember, it doesn't matter about the order for this one. We're just tossing the 3 and how do they come out. So we got tails, heads, heads. We got heads, heads, heads. We can also have tails, heads, and tails. We can also have heads, tails, and heads. 1, 2, 3, 4, 5, 6. What am I missing? Tails, heads, heads. We can have heads, tails, tails. And then we can have heads, heads, tails. So there's our sample space. Now, if we let the random variable, like we said earlier, equal x, which equals the number of heads, based on our sample space, we can get a probability distribution table. Well, based on our sample space, how many times do we get 0 heads? Oops. So 0, oh my gosh, 0 heads. 0 heads, well, we've got 0 heads here. And that's really it, right? That's the only time in our sample space where we ended up with 0 heads. So 1 out of 8. Question is, how many times do we have 1 head? So 1 head is right here, right here, right here. So we've got 3 out of 8. How many times do we have 2 heads? 2 heads we are right here, and right here. So we've got another 3 out of 8. And how many times do we have 3 heads? That's that guy, 1 out of 8. So this right here is basically our probability distribution using the sample space and identifying this random variable x. Now, we are not performing this experiment, right? We're using the theoretical of what could possibly happen. What could possibly happen when we toss those 3 coins. So let's construct a probability distribution for rolling a balanced die. Just basically means a die with 1 through 6. So what is the sample space for one dice? You got 1, 2, 3, 4, 5, and 6. So if I let the random variable, we'll call it x, equal the value on the die, which is 1, 2, 3, 4, 5, or 6. So those are going to be all of my random variables. According to this, the probability of getting The probability of getting 1 is 1 out of 6. The probability of getting a 2 is 1 out of 6. The probability of getting a 3 is 1 out of 6. 4 is 1 out of 6. 5 is 1 out of 6. 6 is 1 out of 6. So we're not really doing anything different here, right? Now the question is this is when you have to make your own probability distribution based on your theoretical probabilities. Sometimes you're going to be asked to actually perform the experiment by using your calculator to get these random variables and then write down the actual probability, the actual outcome. So a few things about probability distribution requirements. What are your observations about these tables? Okay. I hope you notice that the sum of the probabilities in the table must add up to 1, right? That is a key. That it determines that this table is an accurate probability distribution. And then the other thing is that the probability of each event must be between 0 and 1. And 0 and 1 can be included. You can have a probability of 0, or you can have a probability that, this is going to happen all the time. So all of these probabilities right here, when you add them up, they must equal 1, and each of these values has to be between 0 and 1. So how does this tie into the probability that we were talking about in the first unit? Still the same stuff. We're just putting it now into a table, okay? Now this idea of random variable, it helps us perform the experiment electronically. So let's determine whether the distribution is a probability distribution. So what do we need to check? We need to check 2 things. Is the sum of the probability equal to 1? And do all are all of the P, well, in this case, it's going to be Y, right? They called it Y. Are all the P's, the probabilities of that event Y between 0 and 1? Well, yes, on the second part, right? Each of these is between 0 and 1, so we're good on that. And when you add all of these up, do they equal 1? Well, we know we need this to be a 16, so that's a 4. This to be a 16, that's a 2, so that's 4 plus 2, 6, 7, plus 9 is 16 out of 16. So yes, that equals 1. So is this table a probability distribution? Yes, it is. Is the second table a probability distribution? Well, right off the bat, no, it's not. Why? Because P of X equals a negative 1.0 for the random variable 1. And it can't be greater than 1, right? So these two things basically tell us that this is not a distribution, probability distribution. Next one, why is this guy? Well, it passes that all of these are between 0 and 1, so that's a yes. But if you add all of these, what do you get? 5, 6, 7, 8. You got 1.2. So no, because the sum of P of X is greater than 1. And remember, this notation right here means sum. Okay, maybe we'll talk about it, but you don't really have to know it. All right, I'll let you guys do the last one. All right, now this part right here, determine whether the distribution is a probability distribution, a function example. Well, they're telling you what x's are, what the x's are. You just got to make a table and check the rules up top. So when x is 0.1, when x is 0.02, and when x is 0.04, what is P of x? Well, just take that, plug it in. 0.1 plus 0.1, that's 0.2. 0.02 plus 0.1, that's 0.12. 0.04 plus 0.1, that's 0.14. So now, is this a distribution? Well, we're checking again. Does the sum equal 1? And is each value between 0 and 1? Well, this passes, but obviously this does not. The sum is less than 1. Okay, because when you add these guys up, you end up with 0.46. So the sum is less than 1, therefore, no. It is not a probability distribution. I'll let you guys do the next example. And then the last thing is constructing a graph for the probability distribution of tossing the 3 coins. This is just going to be a bar graph. And on the test, you will be asked to graph this data. And you will be, every part of this graph will be checked. So go back to elementary school when you first learned how to graph. We know this is the x curve. This is going to represent P of X. Down here, we've got the number of heads, because that is what our variable is. And over here, we've got our probability. We are graphing 0, 1, 2, and 3. So 0 is going to be, well, 0 heads, right? So 0 heads is going to be on, I'm going to have to do it like right here, we'll call this 0. Remember, this is a bar graph that represents, let me fix that. This is a bar graph that represents the number of heads. So technically, 0 number of heads is right over there. We've got 1 head, 2 heads, or 3 heads. So 0, 1, 2, and 3. So question is, what is the probability of getting 0 heads? Let's write down our 1/8, 2/8, 3/8, right? 4/8, which we are not going to need, but let's draw our graph. So 0 is 1/8. 1, and you can fill that in if you want. 1 is 3/8. Okay, it's not easy for me to draw these straight lines. 2 is also going to be 3/8. And 3 is going to be 1/8. And that is our probability distribution for tossing 3 coins. Now, writing the probability distribution as a function, we're going to leave that for the next section, but I'm going to write it down right now just so that you can see where we are going with this. So we've got 3 coins combination because order does not matter. And X is going to be representing the 0, 1, 2, 3, and 4. And our sample space was out of 8. And X was equal to 0, 1, 2, 3. Okay, so this is extended, not needed to know, a nice to know for later. All right, that's it.